Hi there. In this video, we're going to be learning about random variables. The technical definition of a random variable is that it's a function that assigns values to each of an event's outcomes. It does not have a fixed value. Now, if you don't completely understand that definition, that's fine. Most people learn with examples. But one thing, an important thing to get out of this is that it doesn't have a fixed value, which means that it varies. In other words, it's a variable, as it says. We will touch on that again in a bit. Now, the other thing you should know is that it's denoted by a capital letter, usually an X. So sometimes we use Y, Z. Those are other common ones. In fact, you could use any capital letter, but we normally stick with X. But do bear in mind that you can get questions with other letters, or you could have to create random variables sometimes, and you can't always use the same letter. So that's why you need to know you also have other capital letters that are used. Alright, so let's look at an example of a random variable. So X can be the score on a dice, for example, or the result of a coin toss. It can be a lot of other different things, but these are two examples. Now, just bear in mind here that we're not actually saying what the score on the dice is. We're just saying that X is a random variable that denotes the score, whatever it may be. In other words, there's no fixed value here. Okay? And here I say, remember, X doesn't tell us the actual score on the dice. For that, we need a lowercase x, or for example, if we're using Y, be Y, lowercase y, and a capital Z will go as a lowercase z. So, we will talk about the lowercase on the next slide, so don't worry about that. Now, the next thing is that it can either be a discrete random variable or a continuous random variable. So X, if it's discrete, it means it can only take certain values. For example, the score on a dice, that can only take values from 1 to 6, integer values. So it's discrete. If it's continuous, it can be a multitude of different values. For example, someone's height can be any value you can think of, whereas discrete would be more something like the score on the dice, or people's height rounded to a specific number. It doesn't have, just because it's discrete, it doesn't mean that it's always integer values. For example, you could have a spinner with values 1, 2, 3, and 4.5, and that would still be discrete because it can only assume those 4 values. So that's the difference between discrete and continuous random variables. In this video, we're only going to deal with discrete random variables, but later on in year 2, you will learn about the normal distribution, which uses continuous random variables. So now that we've looked at what random variables are, let's actually do something with them. So what this px here is called, or in other words, it's p capital X equals lowercase x, it denotes the probability function. What is the probability function? Well, it's a formula that generates the probabilities for different values of lowercase x. So it will give the probability of a certain event occurring. Now this capital X, we already know that denotes our random variable, like so. And this lowercase x is a particular value particular value that x can take. That x can take. Alright, so again, this will be more clear in an example. So here, it says, if x denotes the score on a fair dice, what is the probability of x equals 3 and the probability of x equals 7? Okay, so let's see what we have here. So we know that x, our random variable, denotes the score on a fair dice. Right, so we know that it's just 1 to 6 integer values. And now here we have two values for lowercase x. We have 3 and we have 7. So those are the particular values that x can take, capital X. Okay, so to find the probability function p x equals 3, well, that basically says what's the probability of getting a 3 on the score as the score of on a fair dice. Or remember, this x purely just denotes the score on a fair dice. We only use x as a shorthand, but these two would actually be the same. So what is the probability of a score on the fair dice being 3? Well, it's a 6, isn't it? Because you have 6 sides and we only want one of them. And now px equals 7, or the score on a fair dice equals 7. Well, you can't get a 7 on a normal fair dice, so it would be 0. Just like that. So now, hopefully, it's becoming a little bit more clear as to what this actually means. Random variable isn't a fixed value, but you can fix lowercase x to it or other values to it and get a probability. Alright, let's move on. So a probability distribution is a table showing the possible values of x and their respective probabilities. There are many probability distributions, but some special ones we'll learn in detail are the binomial distribution and the normal distribution. The binomial being a discrete distribution or using discrete random variables, and normal distribution using continuous random variables. So all of this links in with these random variables, and but the probability distributions we're going to be learning about in this video aren't going to be these two. They're going to be different ones that we can create. Alright, let's move on. Okay, so this example says the random variable x, where x can only take values 1, 2, 3, has the probability function px equals x equals kx for x equals 1, 2, and 3. Find the value of k. Okay, so this sounds like a lot of x's and k's, and you might not know where to start. But what we want is the value of k here, don't we? That's our goal. And we're given this probability function, and we know that x can only take values of 1, 2, 3. So, what we can do is if we make a table of x, and then have our different values in it, 1, 2, and 3, and then we find out what the probability function will be, then we can actually figure out what k is. So let's figure out what it'll be. So when x is 1, kx will be just k, because x is equal to 1. When x is 2, then we'll have 2k. And finally, when x is 3, we'll have 3k. all I've done is substituted the value of x into the probability function. Now you might be wondering, how can we find k from this table of values? Well, we can use a nice little rule, which is this. If we get all values of x, so in this case it will be 1, 2, and 3, and we sum the probability function for all of them, we'll get 1. Now this makes sense because if you add all of the values that you can possibly get out of an event, all the probabilities, if you add those together, you'll get 1. For example, if you are rolling a dice, if you added the probabilities of getting each number and if you added all those together, you get 1. So what can we do with that? Well, if we add all of these probabilities that we found, that's all of the values, because it can only take values 1, 2, and 3. So that means we can actually use this formula. So we have k, or in fact, let's be even more abstract for now, but use this formula. So we're going through all of the lowercase x here. So we're going through 1, 2, and 3, like that. We're just adding them all together, and that'll equal 1. And then we can put our values in, like so. We get, if we add these together, we get 6k on the left, and we just divide through by 6 to get k equals a sixth. And we found the value of k. And this table that we've drawn, this is actually our probability distribution. So if you've actually learnt about the binomial or the normal distribution, and those aren't actually the only distributions you've learned. For example, this here is a probability distribution in itself. It's just the normal and binomial, we learn how to do different things with them, and they're really useful. That's why. But yeah, this itself is a probability distribution. Okay, so here here the example says that the discrete random variable x, where x can take values 0, 1, 2, 3, and 4, has the probability distribution shown below. And we're actually given the table this time, and it says to find the value of a, so this here, to find the probability of x being between greater than or equal to 2 but less than 4, or in other words, the value that the random variable takes should be in that inequality. And it also wants us to find the mode. So let's work through this in order. Oops. Wrong color. There we go. So let's find the value of a. We can use the same rule that we learnt last time. If we add up all the probabilities together, we'll just get 1. And if you think about it, these are all the values it can take, because it tells us here that it can only take these values. So then, what do we get? Well, when we add all of these together, we get 0.8 on the 0.8 plus a equals 1. And then we can just subtract that 0.8 to give us a equals 0.2. Alright, so actually let's fill that in like so. Now, B says find the probability that x is greater than or equal to 2 but less than 4. So what we're looking at here is we want it to be greater than or equal to 2, so we want to include 2, and 3 is also in the inequality, but 4 isn't, because it's just less than. So all we need to do is, we know that this here is equal to the probability of x equaling 2 plus the probability of x equaling 3, but not 4. And because it's discrete, we know we won't get any 2.5s or 3.5s. These are the only values that are possible in that inequality. So let's add those together. That's not, the probabilities are 0.3 plus 0.2 gives us 0.5 as our answer. And finally, it wants the mode. Now the mode is purely, if you go back to learning about the mode, median, and the mean, and stuff like that, the mode is the most popular value normally. In this case, it's the one with the biggest probability. So in this case, the mode equals 2, because 2 has the highest probability of occurring, with 0.3. Okay. Right. So this is another example, maybe a tougher one. It says that an unbiased 6-sided dice has faces marked 1, 1, 1, 2, 2, 3. The dice is rolled twice. Let x be the random variable sum of the two scores on the dice. Show that the probability of x equals 4 is 5 over 18. And then we need to find the probability distribution of x. Alright, so let's break this down a little bit. So we have here, we know that we're rolling an unbiased 6-sided dice. We know what faces it has. And we know that it's rolled twice. And we want that x, we want x to be the random variable that it's the sum of the two scores on the dice. So we should probably find out what x can be before we go to find x equals 4. But before that, we can try a few different things. For example, we could say, okay, how can we get 4 as x? So how can the sum of the two scores on the dice be 4? Well, we can get 1 the first time and then 3 the second time. We can get 2 both times, for example. So now we have an idea in our head of what we're looking for a little bit. But there are two methods when we're involving multiple random variables. There are really two methods that you should keep in your head. One is tabulating all of the possibilities. So what we can do is you can put a plus sign here and tabulate these results, which basically means put the values you can get with the first roll. So this is the first roll. With the values you can assume with the second roll. Like that. Now what we want to do is we just want to add each column to each row. So 1 plus 1 is 2. And we have 1s all the way through here. So we can actually just fill that out. Now we just add 1 to each of these values, so we get 3, 3, 4. And again, that's the same. And then here we have 2 plus 1, which is 3. Oh, we're adding 2 to all of these values. Feel free to do this yourself if you want assurance that it's correct. Now we're adding 3 to each, like so. Okay. And now that we've done this, we can actually say, wait, these are all the values that we need. So there are 36 possible values here, because it's 6 times 6. Now, which one of these will get us our 4? Well, we have this group of 4 here. We have this group of 3. We have this group of 3. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values. So the chance of x being 4, which again is the sum of the two scores of the dice, is the probability of getting a 4, which is 10, over the total probability, which is 36, because there are 36 possible outcomes. And we can simplify that by halving the top and the bottom to get 5 over 18. as required. And now we want to find the probability distribution of x. So, as always, we'll put x on the top and probability of x, of capital X equaling x on the bottom. And now we can put in each of the values of x. So we have 1, 2. In fact, we don't even have a 1. We have the lowest value we have is a 2. And then we have a 3, 4, 5, and a 6. Okay? And remember, the reason why we don't have a 1 is because we're finding the probability distribution of x, which is the sum of both of the roles. And there's no possibility of the sum of both the roles being 1. So here, we get 9 over 36 for the 2's because there are 9 2's. So we can simplify that to a quarter. With the 3's, we have 6 plus another 6 here. So we have 12 out of 36, or a third. We already know 4. Now 5, we have 1, 2, 3, 4 out of 36, or 1/9. And finally, we just have 1 out of 36. 6. And what we can do to check this is we can actually just add the probabilities together. And if we get 1, we know it's correct. Because of the rule before. Now, sorry, this was question B. Now the second method, we can actually is a little bit more difficult. So if this is new to you, you might want to just stick with this method for now. But there are questions in the future where this method 2 will be very useful. And that's if we make some new random variables. So we can say let x1 be the score of the first dice roll. Let x2 be the score of the second dice. I should have probably said that they're random variables as well. Whoops. Okay, so now we have these 2 new random variables. So let's find the probability distribution of any one of these random variables. So let's do x1. Remember now this will be different as well. Whoops. So yeah, there we go. So we can actually only get 3 values here. And because it's unbiased, we know that we have a 3 out of 6 chance of getting a 1 or a half. 2 out of 6 chance of getting a 2 or a third. And a 1 out of 6 chance of getting a 3. So this is for x2 as well, because x1 and x2 are the same dice, so it doesn't really matter. And so they have the same probability distribution. So now that we know the probability distributions of the both 2 of the dices, let's see what values of x we can, lowercase x1 or lowercase x2 we can get to get 4. So for example, x1 could equal 1 and x2 could equal 3. What else could we have? We could have the probability of x1 equaling 2, probability of x2 equaling 2 as well. And remember, we can also have x1 equaling 3 and x2 equaling 1. It's just the other way round of this first one. So to find this, all we have to do is multiply them together. So that will be a half times a sixth plus a third times a third plus a 6 times a half. And then that, if you work all of that out, that will give us 5 over 18. Now, I only did A with this method, but you can do all of them. In this case, I would definitely go with method 1, but in the future, it might be easier in some questions to use method 2. But if you don't understand method 2, it's fine. Okay, now let's talk about the cumulative distribution function. And it's denoted by this capital F x. And it gives the probability that x will be less than or equal to a value, with that value being what's inside the bracket. In other words, we have this. Fx0 equals the probability of x being less than or equal to x0, which also equals the sum of all x less than or equal to x0 of the probability function. Now, again, that's a lot of notation there. So it's always better if we learn it within an example. So on this column, we have the values of h. See, we're not using x this time, so I can show you that you can have different letters. It's not always x, and it still means the same thing. So h is our random variable here, and this is our probability function. Right? And this here is our CDF, or our cumulative distribution function. So we denote it like that. So now, let's think about, now we have the probability distribution here. We know what they are for each of the values of h. So now let's find the cumulative distribution function using this. So now we have fh, not xo, because we're using h. Okay, and that will equal the probability of capital H being less than or equal to h. Let's sub in our value of h, so it's 0.1 in this case. And now we just want to add all of the values of h before 0.1. Or less than or equal to 0.1. That's basically what we want to do. But the only one we have is 0.1. There's no value of h less than 0.1. So that will just be the probability of h equaling 0.1. In other words, a quarter. Now you don't need to put all of this notation in every time. For example, here we want the cumulative distribution function of 0.2. So we can say, okay, so that's the probability of h being capital H being less than or equal to 0.2. In other words, it can either equal, it's so easy to just write x, 0.1 plus the probability of h equaling 0.2. In other words, a quarter plus a quarter, or a half. And similarly, you can continue like that. So this time, it will be less than or equal to 0.3, so it will be a quarter plus a third, or a half plus a third, which gives us 5 over 6. And then finally, we add 1/6 onto that to give us 1. And you can see that it always ends in 1 with cumulative distribution function. Because once you add, if you've added all the probabilities together, then it'll equal 1. So in this case, we've added all of the probabilities by the end. And so we've got a 100% chance. It's like saying, what's the probability of getting 0.4 or less? Or h being 0.4 or less? Well, that's every single possibility. So of course it's going to be 1. So you can see that the cumulative distribution function is actually a lot like the cumulative frequency. So if you cast your mind back to when you learned cumulative frequency, you have all the frequencies, and then the cumulative frequency just adds each frequency on to the previous amount. And that's the same thing that we're doing here. Okay, so let's do one last example. So for a discrete random variable x, where x can only take the values 1, 2, 3, and 4, the cumulative distribution function is fx equals kx for those values, find k, and the probability function. So this actually looks a lot like the example we did earlier, but the difference is now we've got the cumulative frequency, not the probability function. Sorry, not the cumulative frequency, the cumulative distribution function. And now we know it's only for 1, 2, 3, and 4. So what we want to do first is we want to find k. So how can we do that? Well, we can use the rule that we kind of learned before, which is the last value of a cumulative distribution function will be 1. Because it adds all of the probabilities of all the possible values. So in this case, that would be 4. So if you find f4, well, we're substituting x as 4, so we get 4k, and we know that that's equal to 1. So in other words, we can divide by 4, we'll get k equals 1/4. Okay, great. So now we want to find the probability function. Okay, so let's do that. What we want to do is we can now actually write this differently. We can write fx to equal 1/4 x, like so, because we've now found out what k is. And now what we can do is we can just find the different values of the cumulative frequency. So here I've made a similar table to last time. So now what we can do is when x is 1, 2, 3, and 4, we can now find out what this is. So if we use this formula here, when x is 1, we substitute x as 1 and we get 1/4. And then when it's 2, it's 1/4 times 2, so it's 1/2. And then so on and so forth, we get 3/4 and 1. Now you can see it's kind of like what we did last time, but it's the other way around. This time we have this column and we're trying to find this rather than vice versa. So now let's figure out what it is. So again, remember this first one will be the same if we're thinking because it's cumulative. And the second one, we want to see how much it takes to get from 1/4 to 1/2. Well, actually, we add on 1/4. So we can do that. And then again, we add on 1/4 here. So it must be 1/4. And then we finally add 1/4 again. And there you go. We've got the probability distribution. But it wants the probability function. So it wants a function for what px equals x is. Well, what we can say is that it's always 1/4. No matter what value of x you put in. Alright. Now, here are some exercises. There are 3 to have a go at. The first 2 are things that you've looked at. But the third one is a little bit trickier. So, good luck.